Hey everyone, today we are going to solve LeetCode problem number 300, longest increasing subsequence. It's a very important question and has been asked in a lot of companies. In this problem, we are given an array of integer which is nums and we have to return the length of longest strictly increasing subsequence. Okay, so let's try to understand using an example. Let's say this is the example and we have to find the longest increasing subsequence. Let's first try to understand what is subsequence. So any two elements where I is less than j, like C1, 0, 3, these three. This is a increasing subsequence. Or you can say 1, 0 and 2, 3. This is also a subsequence where we are picking the items in the order of its index. Their indices are in increasing order. What we have to find is this is the subsequence, and the second quality is it should be increasing. This is not increasing, this is not increasing. If I take 2 3, 2 3 is a subsequence which is increasing. Yeah, or you can say 1 2 3, 1 2 3 also increasing, but we also have to find that it is a longest subsequence in this array. So here if I consider 1 2 3, this is the increasing strictly increasing subsequence, but this is not the longest. Longest should be this one, 0 1 2 3, 0 1 2 3. So this is my longest increasing subsequence. So what we have to return is we have to return the length of this LIS in this array. Okay, let's take another example. Here, what is the longest increasing subsequence? If we take 2 5 1 0 1 2 5 7 and 18, 2 5 7 and 18, this is the strictly increasing subsequence of length 4. Or if I take 3 7 1 0 1, no, I won't able to get length 4. The second possibility can be 2 3 7 18. This is also longest increasing subsequence of length 4. If I start from 10, 10 is the subsequence of length 1 and it's strictly increasing, but this is not the longest. Okay, so how do we approach this problem? The one thing is like we think in terms of recursion, that at every index, let's say we are at index 0, if we take the element or we do not take the element. If we take the element, we also have to check whether this element is bigger than the previous one or not. And if we are not taking the element, we can just move straightforwardly. Okay, so at every index, if the current element is not greater than the previous one, we will just discard that call. If that is greater than the bigger one, we have two options: either take that element or do not take that element. So at every position we have these two options. So it will go 2 raised to power n. But if we memorize the solution, how do we memorize? I think two variables will be there: the previous element and the current index. So if we memorize the solution over these values, it will give us an optimized approach, which is a recursion with memorization. But this is going to be add a lot of complexity. Let's keep it simple and go in a bottom-up approach. 2 1 0 3 2 3, 0 1 0 2 3 2. What is our strategy to go in terms of bottom approach? We will try to tackle the smaller problem first. What is the small problem? Finding LIS of this 0 only, and then finding LIS of 0 and 1, when finding LIS of 0 1 0. So for this 0, LIS is 1. It is strictly increasing and of length 1. For this, if we take 0 and 1, the LIS is 2. Because 1 is greater than 0 and both will be considered in our subsequence. So for this, what is the LIS? LIS is 2. So how I'm figuring out this? I'm memorizing the solution for every sub problem or smaller problem. 0, 1, 0, 2, 3, 2. This is our given array. If I take a DP array to store our solution, first of all, we know that every element, if I take only one element, that is a subsequence, and that is of length 1. So first of all, every element is making a subsequence of length 1, which is strictly increasing, right? Now we have to just find the longest increase subsequence. Let's tackle this smaller one, 0. For 0, we don't have any previous element, so it will remain 1. For 1, what I can check is whether adding 1 is making any significance or not, whether we should consider 1 or not. So for all the element smaller than 1, we will see what is the longest increase subsequence we can get from this value, and over that we will see if I add 1 in it, what benefit we can get. So if we have to add 1 to this, we will be adding 1 after that element which is lesser than 1. So 0 is less than 1. So for 0, LIS is 1. So LIS which is ending at 0, we can add 1 to that. So it means by adding 1, we can get LIS of length 2. Okay. Now to this position, our LIS value is 2. Maximum LIS value we can get is 2. So now we will see whether we can add 0 and make our answer effective. We will start from 0 to current index and see if any element is less than the current element. No element is less than the current element, so it will remain 1. Now we are at 2. Any element which is less than the 2, 0 is less than 2, yeah. After 0 we can add 2. In that case the LIS will be 2. After 1 can we add 2? Yes. So in that case LIS will be 2 plus 1, which is 3. So after 0 if I add 2, it will be 2. So maximum of these 3 is 3. So 3 is the longest increase in subsequence if I consider 2. 0, 1. So for 0, 1, 0, 2, maximum value is that LIS value is 3, which is 0, 1, 2. Okay. Now our smaller problem is this one, 0, 1, 2, and we are at this index. Here we will see after what are all the elements after which we can add 3. We can add 3 after all the elements, so we will see the value of maximum LIS of any one of these value. So for verse 0 it will be 2. If I add 3 after 2 it will be 3. If I add 3 after this 0 it will again be 2. If I add 3 after this 2 it will be 4. So if I adding 3 as well, so collectively this subarray is giving me LIS of 4, which is the 4 length element, which is 0, 1, 2, 3 are the elements which are strictly increasing and the longest so far. So 4 is coming here. Now we are at 2. So we can add 2 after this 0. It will be 2. After 2. After this one it will be 3. After this 0 it will be 2. After, and cannot add after this 2 and 3. So maximum is 3. So if I consider this 2 in the LIS, it is 3. So what is we are storing at DP? That from index 0 to index I inclusively, I should be there. What is the maximum value of LIS we can get? So what is the LIS we will get if I AND at this 0? What is the LIS I can get if I AND at this one? If I AND at 0, if I AND here, if I AND at this 3, it means that 3 is the last index in my LIS. So the maximum of this DP array is going to be our answer. So what is the time complexity here? The time complexity is, let's say if I take another example, 7777. In the starting, what is the LIS? It's up to you whether you want to initialize it with one or not. So let's say for the first element, no previous value. So we'll consider that 0. So keep it 1 for both this 7. Any element which is less than 7, no. So it will remain 1. So for this one, we will see any element less than 7. This will remain 1. For this 7 also, we'll check if there is any element which is less than 7. No. So it will remain 1. So LIS is 1 in this case. But the time complexity is n square. Because for each element, I'm checking all the previous elements. Let's say for every ith element, I'm checking minus 1 elements. So it is going exponential. Now let's code the n square problem. Then later we will see whether we can further improve this time or not. Let's capture the length of the array, nums dot length, and capture the answer. Answer is going to be the maximum value in our DP array. So I'm taking a DP array, new int of size n, where I will store the longest increase in subsequence value stopping at that index. So I'm going from starting to end, from I equal to 0 to I less than n, I plus plus. I will capture the maximum value. Maximum value we have captured before that index. So let's say that is 0 in the starting, because li's value for any element is 1, so it won't be less than 1. So for j equal to nums of j is less than nums of I. If that element is less than the nums of j, in that case their dp value we will capture. So maximum equal to math dot max maximum and their dp value, dp of j. Okay, now we have the maximum value. So let's say closing at this position, this 0 position, what should be the value? The maximum value we have captured by taking the elements previous to that plus this current element itself. So dp of I is equal to, we are considering the current element plus any lesser element with the maximum dp value, which is max. And while capturing that, we can also capture our answer here. If dp of I is greater than answer, in that case answer is equal to dp of I. Check our sample test cases. Sample test cases are passed. Submitting the problem. Submitted successfully. Hope you understood the problem. We coded in the bottom-up approach using a DP array where the time complexity is going n square. We are also asked a follow-up question. Can we come up with the algorithm which is running in n log n time complexity? Okay, now let's discuss our second approach where we will be finding the LIS of this array using patient sort algorithm. Using patient sort algorithm, we can find the longest increases subsequence in n log n time, where we have to minimize the number of piles, and we are going to create piles using binary search. Let's say first of all we are coming with 10. 10 we have inserted. Now we have 5. We will check at which location we should insert 5. So 5 will be inserted at the location where 10 is present. So 5 will insert here. So we will now see where we have to insert 8. 8 should be inserted after 5 in the next pile. Where we have to insert 3. 3 will come here. 9. 9 will make a new pile. 4. 4 will come here. And now where the 12 will come, 12 will create a new pile, and 11 will come here. So here you can see we have 4 pile, and all the piles are in the sorted order. So what does these pile element are representing? That every element is a part of increasing subsequence where the length is given by the pile index. So till 4 we are having increasing subsequence of length 4, of length 2, sorry. Index is 0, 1, 2, 3. So 4 is making a increasing subsequence where the length of the increasing subsequence is 2. So 9 is making an increasing subsequence where the length is 3. And 11 is making an increasing subsequence where the length is 4, sorry. So from 11 to 9 to 4 to 3. 3, 4, 9, 11 is our longest increasing, one of the longest increasing subsequence. So okay, so this was our patient sort algorithm where we are picking every element, that we are picking an element and we are inserting in our piles using binary search algorithm. Using binary search we will find the insertion point, and on that insertion point we are going to insert the element. So for binary search we are using log n time and we are processing it for each element. So in this way we are using log n time for this process. So this was the second optimized approach to find the length of longest increasing subsequence using patient sort algorithm. Let's code this as well. Here first of all we have to prepare piles from our given input array. Let's firstly capture the length nums dot length and also track the number of piles. Number of piles in the starting is 0. For the piles I can take another array, piles of new integer. Let's take it of n size. I have taken n size array, but I will capture the number of piles in a separate variable so that I can return that in the end. And in the end I will be returning number of piles, and those number of piles will give me the length of longest increasing subsequence. Okay, now process every element. Int num of nums. Now let's see at which pile we have to add this element. Destination pile. And what is the destination pile? For that we are going to use binary search. Arrays dot binary search. What we have to pass for binary search? The array, piles array, and the starting index is obviously 0 and the ending index is number of piles. So from 0 to 0 it will search the num item, num will be searched from 0 to 0 location in piles array. Okay, if it is found then it is fine. If it is not found, what we will get is minus. We can add our num element. Okay, we will also check whether we are increasing the number of piles or not. So for that what we can see is if the destination pile is equal to number of piles. Let's say for the first time the first element is being inserted at a 0 index, but we had no pile. So number of piles equal to destination pile. In that case number of piles will be increased, and in the end we can directly return number of piles array, and we did the binary search and check for the location, and if the insertion location is equal to less number of piles, we are increasing the number of piles, and in the end we can return number of piles. Okay, let's try to test over sample test cases. There was a typo. Okay, it should be minus destination pile plus 1, like this. It should be like this because insertion point is binary search return value is minus insertion point minus minus 1. Okay, so we have to find the insertion point. So it would be, let's say we are returning index, so index plus 1 and minus in the starting for both values. Okay, so it should be minus destination pile plus 1. Now let's test again. Okay, testing is done. Submitting the problem. Submitted successfully. Now it is way faster than the previous solution. Hope you understood the problem. Thank you guys.